In a standard hydraulic circuit, our eyes naturally gravitate toward the heavy machinery. We see the motor driving the pump, control valves directing flow, and the massive steel cylinder lifting. But this solid hardware is useless without the fluid pathways connecting them. This fluid functions as a highly engineered, dynamic structural component. To function efficiently, this liquid has to simultaneously satisfy dozens of strict physical parameters, many of which directly oppose one another. Failing to maintain those parameters breaks the machine. Empirical data shows that contamination and physical degradation of the fluid account for up to 70%. Mastering the exact physical properties of the fluid itself is the absolute prerequisite for designing any viable hydraulic circuit. We define a fluid as a continuous medium with no internal voids. To understand how this continuous volume moves, we mathematically model it as parallel layers stacked on top of one another. Applying mechanical force parallel to that top layer generates shear stress. This causes continuous deformation. The top layer flows, dragging the layers beneath it to create a staggered velocity gradient. In theoretical physics, an ideal fluid is a frictionless scenario where neighboring layers offer zero resistance to sliding. But ideal fluids do not exist. In reality, the layers offer intense physical resistance to their neighbors during deformation. We call this internal friction viscosity. This internal resistance dictates exactly how efficiently mechanical energy travels through the liquid medium. In a working circuit, the fluid faces immense direct compressive forces acting upon the entire volume. Compressibility is how much the fluid yields to those compressive forces, resulting in a measurable change to its volume. We measure specific resistance to that volume change using a metric called bulk modulus. Hydraulic systems require fluids with an extremely high bulk modulus, remaining practically incompressible under immense pump force. If the bulk modulus is too low, the fluid acts like a liquid spring, absorbing and storing mechanical energy, leading to sluggish actuator responses and dangerous springback effects in the cylinders. Treating the fluid as a rigid, incompressible medium through a high bulk modulus guarantees that any displacement at the pump instantly moves the load at the actuator. Stepping back to the macroscopic scale, we can see exactly why the fluid is placed under such extreme physical demands. It has to execute several distinct tasks at the exact same time. Because of its incompressibility, its primary job is transferring pressure undiminished across the system, fulfilling Pascal's law. But it must also provide hydrodynamic lubrication. Close-fitting metallic components, like gear pump teeth, rely entirely on a microscopic flowing fluid film to prevent metal-on-metal contact. Furthermore, friction and energy conversion generate massive amounts of heat. The fluid must absorb this heat and carry it away to be cooled. It cushions against violent pressure oscillations, flushes away microscopic metallic scuff, coats internal parts to prevent corrosion, and accurately transmits control signals. The fluid operates simultaneously as the mechanical powertrain, the thermodynamic coolant, and the chemical protector of the entire machine. Fulfilling all these roles requires engineers to treat fluid selection as a strict optimization problem, balancing entirely contradictory physical limits. This chart compares viscosity against temperature. If viscosity drops below a specific threshold, the liquid becomes too thin. Lubricating films break down, causing immediate mechanical wear. Conversely, if viscosity remains too high, the fluid becomes too thick. The system wastes power fighting internal friction, dropping the efficiency of every component. A viable hydraulic fluid must possess immense viscosity temperature and viscosity pressure stability to stay within the narrow optimal middle zone. Standard petroleum-based oils handle this well, but extreme heat or harsh chemical environments often require specialized synthetic fluids to maintain stability. However, these synthetics introduce their own engineering trade-offs. They are significantly more expensive, and if they leak, they can chemically melt the external insulation on electrical cables. Yet, regardless of the fluid type selected, the ultimate operational threat to the system's survival is always contamination. This brings us back to that critical empirical baseline. Up to 70% of all hydraulic failures originate from particulate matter and degraded fluid. The introduction of water, trapped air bubbles, or solid matter destroys the carefully calibrated bulk modulus and viscosity that engineers rely on. Because of this, mitigating faults begins early. Strict cleanliness protocols, often requiring specialized dust-free rooms, must be enforced during the initial assembly of hydraulic units. All the advanced kinematic engineering of the fluid and the precision manufacturing of the pumps and valves are instantly voided if rigorous physical cleanliness is not maintained. Returning to a complete hydraulic schematic, we see how the fluid's state dictates the behavior of the hardware. We see exactly where shear stress, viscosity, and bulk modulus dictate the performance of the pump, valves, and cylinder. The power and speed of this entire circuit are strictly limited by the physical integrity of its continuous fluid medium. Understanding how this liquid actively deforms under pressure and enforcing the contamination controls to protect it is what allows engineers to accurately simulate and predict these complex system dynamics. With the physical properties of the fluid defined, we can now translate these kinematic rules into the mathematics of static pressure. Because before anyone can calculate the mechanical output force of the machine, they must first master the physics of the fluid driving it.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.